if the electric field is in this manner, the direction of the potential will be opposite to it. So obviously it will have the angle is 180 degree. Dielectrics are the insulator type, which does not allow the flow of any sort of electrons and the charges through it is called as dielectrics. Carbon atoms outside and oxygen atom inside, so all three coincides in one single line. That is why it is called as an example for non-polar molecules. Hello everyone, I am Vrinda, Faculty of Physics, welcoming you all to session 1 of chapter 2, Electrostatic, Potential and Capacitance. So in this chapter, we are going to study the important concepts of the concept class, that is equipotential surface. So what is meant by potential at the first? So potential means it is a energy or a work done in bringing a unit positive charge, that is unit positive charge from one end to another end. That is called as your potential. Okay. That means maybe from infinity to certain point or maybe from one end to the other. That is called as your potential. So what is this equipotential surface? If suppose in case you have a surface, the name itself tells equipotential surface. Equally the potential is being distributed on the surface of the charges. That is called as surface of this object. The surface of this conductor is called as equipotential. Equally, the potential is distributed on the surface or superficial area of a conductor is said to be equipotential surface. And the electrostatic potential on the surface of this equipotential surface is said to be 0. The electrostatic potential on equipotential surface is said to be 0. So that's all about your equipotential surface. Before that, you'll have to know what is potential difference and potential. Next is relation between electric field and potential. So electric field turns out to be E vector, potential turns out to be V. Okay. So again, potential is also a V vector because it's a vector quantity. So how exactly we have to get the relation between these things? So you know that what is the potential? Potential difference means it is the work done in bringing unit positive charge. Charge is represented in terms of coulomb. Charge from one point to another point. So this will act against the direction of the electric field. So if the electric field is in this manner, the direction of the potential will be opposite to it. So obviously it will have the angle is 180 degree. So what are we supposed to do? Work done is equal to the force, that is the electrostatic force what you apply, and displacement. The distance between two charges is dr. So it's a vector quantity. So on removal of this vector notation, we have, in order to represent the magnitude, we get E into some trigonometric function has to come with this. So it will be cos 180 degree. So cos 180 is nothing but W is equal to E. That is cos 180 it is 1. So you have E into dr concept. So W is equal to minus E into dr. So this is the dr concept. So potential difference means the work done in bringing a unit positive charge from one place to another place. So suppose if you consider two conductors here and call it as A as well as B. This is A and this is a B conductor. The electric field is flowing in this manner. So this has a potential of V. So the above plate will have potential of V minus certain amount, that is dV, change in potential. So potential energy when it changes, so you have this concept potential difference. So now we have work done in bringing a unit positive charge from one point to another point. So dW is equal to VA minus VB. So what is VA? It is just V. And what is VB? V minus dV. So we have V minus V plus dV. V and V cancel. So what do we have? dV is equal to dW. So this is also the change in work done what has happened here. So now dW and dW, we have two equations. Consider this as equation 1. Consider this as equation 2. On equating two equations, that is equation 1 and 2, you have minus E into dr is equal to dV. So E you retain as it is, dV by dr and negative. This is the relation between electric field as well as potential as given here. One of the important derivations that you'll have to know. That is, electric field is directly proportional to the potential difference. So, relation between electric field and potential is given in that. By using this diagrammatic representation, we derive for the relation between electric as well as potential. So, next is you have potential gradient. So, it is the magnitude, definition of it, potential gradient. So, what is potential gradient? Magnitude of change in potential per unit displacement normal to the equipotential, per unit displacement which is normal to the equipotential surface. This is the potential gradient. This is the equipotential surface to which it is normal. Normal means it is 90-degree surface. At that point, it is known as potential gradient. So, we have E is equal to minus dV by dr according to your previous equation. So, this is termed as your potential gradient. Next, we have dielectrics. So, what are dielectrics? Dielectrics are the insulator type which does not allow the flow of any sort of electrons, and the charges through it is called as dielectrics. So, there are two types of dielectrics. One is polar and another one is non-polar dielectrics. This is one of the most important concept, and this is also called as a non-conducting substance. Dielectric is also called as a non-conducting substance. So, first of all, going to polar molecules. So, point-wise, if you just write, polar molecules are the molecules who shows the dipole moment in absence of electric field also. Okay, and the other thing is the center of positive charge doesn't coincide with negative charge here in case of polar molecules. So, example you can give it as HCl. So, you have H plus molecule here and you have Cl minus molecule here. So, this doesn't coincide with this molecule. That is why it is called as polar molecules. In case of non-polar molecules, again the dipole moment doesn't exist in absence of electric field, and you have positive charge, a center of positive charge and center of negative charge doesn't coincide. And last, you have an example, you can take CO2, wherein you have carbon atoms outside and oxygen atom inside. So, all three coincides in one single line. That is why it is called as an example for non-polar molecules. So, these are the three components what you will have to remember with respect to polar molecules as well as non-polar molecules. Next, capacitance of a conductor. Usually, capacitance means capacitance is observed by a capacitor. And what is the use of a capacitor? It is used to store the charges in order to supply it for the components. So, here we are studying capacitance of a capacitor, before which we will have to know this is the symbol of a capacitor. This is the capacitor plates and this is the extension which has been attached to a circuit. Capacitance SI unit is given in terms of farad. Okay. So, that is the unit of a capacitor. So, what is the use of a capacitor? Capacitor is the one which is used to store the charges. So, we know that since electric field is directly proportional to the voltage which is applied to the potential, so charges is directly proportional to potential is what we can study. So, Q is equal to, removing this proportionality constant, C into V. So, C is equal to Q by V. So C is Q by V in the sense charge can be 1 coulomb and 1 voltage. So how do you define a capacitance of a conductor? It is defined as, or it is said to be 1 farad if 1 coulomb of charge is required to raise the potential for 1 volt. Okay, potential is given in terms of 1 SI unit is known as volt. Okay, so that is how exactly you define the capacitance of a conductor. And next we have capacitor. How exactly the capacitor looks? So these are some of the images with respect to a capacitor. It's a system of 2 conductors which is separated by a insulators, the one which is used to store charges, so that there is no movement, much of the movement of the charges over there. So this is separated by an insulators. Okay, so next you have dielectric strength, which is one of the most important question as well. The maximum electric field that an electric medium withstands without breaking down its insulating property. Okay, so it is a maximum electric field that is which is present, that is a dielectric. It acts as an insulator. Dielectric medium withstands without breaking its insulating property. That is called as the strength of the dielectric. Okay, next you have energy stored in capacitor. So in order to derive this, we will have to know that potential is work done in bringing a unit positive charge, and we have capacitance is given by Q by V. So these two concepts, if you know, it's very easy that you can derive this energy stored in a capacitor. We know that work done is equal to potential into dq with respect to this equation. So how is this given? Work done is equal to V into Q. So there is a change in work done. So it is V into dq. In the place of V, we can substitute V is equal to Q by C. So dW is equal to Q by C into dq. So this is with respect to only one small area or whatever you consider. But suppose if you have to consider the total area of a conductor, because we are checking the energy stored in a capacitor. So if you are considering the complete area of cross section or something, then we have to integrate this into dW is equal to integration Q by C into dq. So now we have W is equal to 1 by C taken out, integration of Q into dq. So this limitation occurs from 0 to Q charge, 0 to source Q charge, 0 to Q charge. So we have 1 by C Q square divided by 2. 0 and Q. Applying limitations, we have W is equal to Q square divided by 2C, because the rest of the things comes out to be 0 and it cancels out. So now what is Q? Q is equal to, since Q is equal to C into V, we can write this as W is equal to C square V square divided by 2C. 1C cancels with C, so we have W is equal to 1 by 2 CV square. So this is the final equation, or you can even write, since we are checking on to the energy stored, so energy can be written as U is equal to half CV square, the potential energy. And this is the final expression. Suppose if you want to continue with respect to any numericals as such, then U is equal to half, instead of C, we can write it as Q by V into V square. This V goes with this, so you will have 1 by Q V divided by 2, or half into QV also you can just write. So this is the other set of equation for your reference. So in today's class, we have dealt with few of the important concepts in the concept class of electrostatic potential and capacitance. Let us all meet in our next upcoming session with the next chapter. Until then, have a good day. Thank you.